The universe is a breathtaking tapestry of light and wonder, filled with glittering galaxies, swirling nebulae, and the gentle glow of distant stars. But beneath its dazzling beauty lies a dark and violent secret: cosmic forces so powerful, so destructive, they could snuff out entire worlds without a second thought. Imagine an object so dense it warps the fabric of space and time, or a blast of radiation so intense it sterilizes planets light years away. These aren't scenes from science fiction. They're real, lurking in the shadows of the cosmos, waiting to remind us just how small and fragile we truly are. Today, we're venturing into the darkest corners of space to uncover the 25 most dangerous objects in the universe. From runaway black holes that devour everything in their path to hypervelocity stars capable of smashing through solar systems like bullets, these cosmic nightmares defy imagination. Some are born from the corpses of dead stars, while others are the remnants of ancient cataclysms, each one a testament to the raw, unbridled power of the cosmos. And the scariest part, many of them are closer than you think. But this isn't just a tour of cosmic horrors, it's a journey into the science behind these apocalyptic phenomena. What makes a gamma ray burst the universe's ultimate extinction event? How could a single quasar outshine an entire galaxy while vaporizing anything that strays too close? We'll unravel these mysteries together, exploring the cutting-edge research that helps us understand, and maybe one day survive, the deadliest forces in existence. So brace yourself, because by the end of this video, you'll never look at the night sky the same way again. The universe is far more dangerous than it seems. And what you're about to discover will leave you in awe. At the top of our list sits the ultimate destroyer, the black hole. Born from the cataclysmic collapse of massive stars, these cosmic voids are so dense that not even light can escape their grasp. Picture a star 10 times heavier than our Sun collapsing inward under its own weight, crushing matter into an infinitely small point called a singularity. Surrounding it is the event horizon, the point of no return where gravity's pull becomes unstoppable. Cross this boundary, and you'll experience spaghettification stretched like noodles by tidal forces until atoms themselves tear apart. But not all black holes are created equal. Lurking at the heart of our Milky Way is Sagittarius, a star, a supermassive black hole 4 million times heavier than the Sun. This monster doesn't just swallow gas and dust, it flays entire stars alive. When a star wanders too close, tidal forces rip it to shreds in a dazzling flare of light, a phenomenon astronomers call a tidal disruption event. Even from 26,000 light-years away, we've observed these violent feasts, reminding us that our galactic center is anything but peaceful. Yet black holes aren't invincible. Thanks to Stephen Hawking, we know they slowly leak energy through Hawking radiation, a quantum quirk that causes them to evaporate over unimaginable timescales. For now, though, they reign supreme as the universe's most efficient predators, lurking in the darkness, bending space and time to their will, and the chilling truth: there could be millions of them drifting unseen through our galaxy, silent ghosts waiting for their next meal. If black holes are the universe's ultimate predators, neutron stars are its most unforgiving pressure cookers. These stellar corpses pack the entire mass of a sun into a city-sized sphere, so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Picture crushing Mount Everest into a sugar cube. That's the kind of unimaginable force at work here. The surface gravity on a neutron star reaches a staggering 1 billion times Earth's, strong enough to flatten atoms into a bizarre quantum soup. But the real terror lies in their volatility. These dead stars aren't peaceful relics. They're seething with pent-up energy, prone to violent starquakes that crack their crystalline crusts. When that happens, the entire star rings like a gong, sending ripples through space-time itself. Astronomers have detected these cosmic tremors from thousands of light-years away, some releasing more energy in a millisecond than our Sun emits in 150,000 years. Then there are magnetars, neutron stars cranked up to nightmare mode. Their magnetic fields are 1,000 trillion times stronger than Earth's, so powerful they could strip the electrons from your atoms from halfway across the solar system. In 2004, a magnetar 50,000 light-years away flexed its magnetic muscle with a blast so intense it briefly ionized Earth's upper atmosphere, despite being farther than most stars visible to the naked eye. These cosmic powerhouses don't just warp space, they rewrite the rules of physics. Get too close and their magnetic fields would scramble your nervous system before their gravity pulverized you. Yet for all their fury, neutron stars are also cosmic lighthouses, spinning at dizzying speeds and emitting beams of radiation we detect as pulsars. They're reminders that even in death, stars refuse to go quietly, and the universe always keeps its most astonishing wonders laced with danger. Lurking between galaxies like cosmic serial killers, rogue black holes are the universe's most terrifying drifters. Unlike their supermassive cousins anchored at galactic centers, these invisible monsters roam freely, ejected by violent cosmic collisions or the explosive deaths of ancient stars. Strip away their accretion disks, those telltale rings of superheated gas, and they become perfect predators, invisible, silent, and utterly merciless. Now picture one drifting into our solar system. At first, nothing seems amiss, just a subtle tremor in the orbits of distant comets, but as it nears, its gravity starts playing cosmic billiards with planets. Neptune's orbit stretches first, wobbling like a top losing momentum. Then Saturn's majestic rings begin to warp, ice particles scattering into darkness. By the time Earth feels the pull, it's too late. Our planet could be hurled into deep space like a discarded pebble, frozen in eternal night, or slingshotted into the sun in a fiery finale. The solar system as we know it would cease to exist not with a bang, but with the cold, indifferent physics of a black hole's appetite. What makes this scenario even more chilling? Hubble's groundbreaking 2022 survey suggests rogue black holes might outnumber galaxies 20-1. That means trillions could be prowling the cosmos right now, leftovers from the universe's chaotic youth when galaxies frequently cannibalized each other, spitting their black holes into the void like cosmic shrapnel. Some might weigh as much as 20 suns, while others rival small galaxies in mass. And here's the twist, we'd likely never see one coming. Without glowing gas to betray their presence, these wanderers reveal themselves only through subtle gravitational lensing. The way they bend light from stars behind them like a funhouse mirror. Astronomers are racing to map these ghosts using star distortions and rogue planet trajectories, but space is vast and darkness hides countless secrets. The next great cosmic predator could already be closer than we dare imagine. Gamma-ray bursts are the universe's most violent fireworks, cosmic detonations so powerful they outshine entire galaxies in seconds. Imagine squeezing the energy of 10 billion suns into a beam no wider than a pencil and firing it across space at the speed of light. That's the raw, apocalyptic power of a gamma-ray burst. These eruptions come in two flavors, each more terrifying than the last. The first, Quasars, are born when massive stars go supernova but don't stop there. Instead of exploding outward, their cores collapse straight into a black hole, launching jets of radiation so intense they pierce through the dying star like cosmic blowtorches. The second type, mergers, occur when two neutron stars spiral into each other in a death spiral, their collision rippling space-time and unleashing a tsunami of gamma rays. A single burst can release more energy in 10 seconds than our sun will emit in its entire 10 billion-year lifetime. That's not just impressive, it's cataclysmic. And if one happened within a few thousand light-years of Earth, the effects would be nothing short of apocalyptic. The gamma rays themselves would arrive without warning, a silent flood of radiation invisible to human eyes but deadly to life as we know it. Within moments, they'd tear apart our ozone layer, stripping away the shield that protects us from the sun's ultraviolet wrath. Without it, Earth's surface would bake under a lethal barrage of UV radiation, triggering mass extinctions, collapsing food chains, and rendering the planet inhospitable for years. Evidence suggests this nightmare scenario might have already played out. 450 million years ago, the late Ordovician mass extinction wiped out 85% of marine species, and some scientists point to traces of radioactive isotopes in ancient rock layers as possible fingerprints of a nearby gamma-ray burst. Even more chilling, the Milky Way hosts stars capable of producing these bursts like Eta Carinii, a volatile hypergiant barely holding itself together. If it goes collapsar, we'd be close enough to feel the consequences. Yet for all their destructive potential, gamma-ray bursts are also cosmic lighthouses. Their fleeting brilliance helps astronomers map the universe's structure, probing the distant reaches of space-time. Satellites like NASA's Swift telescope catch hundreds of bursts yearly, each one a reminder of how fragile our existence really is. The universe doesn't just create life, it holds the power to erase it in a flash, and that's what makes gamma-ray bursts not just fascinating but humbling. They're the universe's way of showing us just how small we are in the grand scheme of things. Hypernova are what happens when a supernova takes cosmic steroids, stellar explosions so violent they make regular supernova look like firecrackers. Picture a star at least 30 times more massive than our Sun, spinning furiously and packed with heavy metals. When this cosmic behemoth reaches the end of its life, it doesn't just collapse, it implodes with such ferocity that the core forms a black hole in seconds, launching jets of plasma at nearly the speed of light. These jets channel the star's entire explosive energy into focused beams, releasing up to 10 times more energy than a typical supernova. The result: a hypernova, an eruption so bright it can outshine its host galaxy for weeks. But hypernova aren't just cosmic light shows, they're the universe's ultimate alchemists. The extreme conditions inside these explosions forge elements heavier than iron, gold, platinum, uranium, flinging them into space like celestial treasure. That gold ring on your finger, it was likely forged in the heart of a hypernova billions of years ago, a glittering relic of one of the universe's most violent events. Yet there's a darker side to this stellar spectacle. Those plasma jets don't just create, they annihilate. If Earth happened to lie within 1,000 light-years of a hypernova's beam, the radiation blast would strip away our ozone layer, bombard the planet with deadly cosmic rays, and trigger mass extinctions. The sheer intensity could ionize the atmosphere, turning skies into a haze of toxic nitrogen oxides. Astronomers suspect hypernova might explain some of Earth's past extinction events. Geological records show spikes in radioactive isotopes like iron-60, possible fingerprints of nearby stellar cataclysms. Even more unsettling is the fact that hypernova candidates like Wolf-Rayet stars are scattered throughout our galactic neighborhood. Some could be ticking time bombs, their death throes capable of reaching across the cosmos with devastating consequences. What makes these explosions so fearsome isn't just their power, it's their unpredictability. Unlike supernova, which signal their demise with neutrinos before the light show begins, hypernova offer no such warning. Their jets erupt suddenly, transforming a distant point of light into an existential threat. And in a galaxy brimming with massive, fast-spinning stars, the next hypernova could already be brewing, a silent reminder that the universe doesn't just create life. Sometimes it comes to take it away. Hidden in the depths of space, quasars are the universe's ultimate powerhouses, the blazing hearts of ancient galaxies where supermassive black holes feast on cosmic banquets. Picture a black hole billions of times heavier than our Sun, surrounded by a swirling disk of superheated gas and dust. As matter spirals inward at nearly the speed of light, friction heats it to millions of degrees, transforming the disk into a radiant beacon visible across the cosmos. But calling it bright would be an understatement. A single quasar can outshine an entire galaxy of hundreds of billions of stars, some blazing with the brilliance of 1,000 Milky Ways combined. Take 3C273, the first quasar ever identified. Despite being 2.4 billion light-years away, so distant its light left when Earth's most complex life was single-celled organisms, it's visible through amateur telescopes as a faint blue dot. What you're seeing isn't just a star, it's the light of a black hole's feast, a cosmic bonfire burning since before multicellular life existed. The energy it radiates in 1 second would power human civilization for millions of years. Yet quasars aren't just luminous, they're lethal. The radiation pouring from their accretion disks includes X-rays and gamma rays fierce enough to sterilize planets thousands of light-years away. Their jets, propelled by magnetic fields twisted to breaking point, can stretch for millions of light-years, punching through interstellar gas like celestial blowtorches. If a quasar's jet happened to point at Earth, the blast would strip our atmosphere bare, boiling oceans and scouring the surface down to bedrock. These cosmic monsters are relics of a bygone era when galaxies were young and black holes gorged on plentiful gas. Most quasars flickered out billions of years ago as their fuel ran low, but their light still travels across the universe, carrying echoes of the cosmos's violent adolescence. Today, astronomers use them as lighthouses, probing the early universe's structure by studying how their light bends through intervening matter. What makes quasars so terrifying isn't just their raw power, it's their reminder that even galaxies have life cycles. The Milky Way's central black hole is dormant now, but given enough fuel, it too could awaken as a quasar, turning our home into a beacon of annihilation. For now, these distant giants serve as both warning and wonder, proof that the universe's most destructive forces are also its most magnificent. Dark matter filaments weave through the cosmos like invisible threads in a spider's web, the hidden scaffolding that holds the universe together. Though they don't emit light or collide with ordinary matter, their gravitational influence is anything but gentle. Picture an intergalactic highway where galaxies glide along these dark tendrils, pulled by forces we can't see, but whose consequences are written across the sky in celestial wreckage. Take the Bullet Cluster, one of the most striking pieces of evidence for dark matter's reality and its potential for chaos. When two galaxy clusters collided at 10 million miles per hour, their visible gas clouds smashed together like cosmic fenders, heating up and glowing in X-rays. But something eerie happened. The bulk of the cluster's mass, detected through gravitational lensing, kept right on moving unimpeded. That missing mass was dark matter, slipping through the collision like a ghostly bullet. The result, a cosmic crime scene where the bullet of dark matter left the gas clouds behind like spent shell casings. These filaments don't just guide galaxies, they fling them into catastrophic mergers. Over billions of years, dark matter's gravitational web orchestrates collisions that can rip stars from their orbits, trigger frenzies of new star formation, or even hurl entire galaxies into the abyss. Our own Milky Way and Andromeda are destined for such a fate, drawn together by the relentless pull of the dark matter filaments between them. When they collide in 4 billion years, the wreckage will birth a new, hybrid galaxy, proof that even the mightiest structures in the universe are puppets to dark matter's invisible strings. Yet for all their destructive potential, these filaments are also cosmic architects. Without them, galaxies might never have formed in the first place. In the early universe, dark matter's gravity created the first clumps, gathering gas and dust until stars ignited and galaxies took shape. The very web that brings chaos also built the stage for life. That's the paradox of dark matter. It's both creator and destroyer, the silent force weaving the universe's grandest designs and unraveling them just as effortlessly. The search to map this hidden network is one of astronomy's greatest challenges. Projects like the Dark Energy Survey scan vast swaths of sky, tracing the subtle distortions of distant galaxies to reveal the filament's gravitational fingerprints. Each new map peels back another layer of the universe's secret blueprints, showing us a cosmos far stranger and more dynamic than we ever imagined. One thing's certain, in the dark matter web, we're all just along for the ride. Vacuum decay sounds like science fiction, but it might be the universe's most elegant apocalypse, a silent, unstoppable transformation where the very rules of physics rewrite themselves in an instant. Picture this: somewhere in space, a tiny bubble of true vacuum forms spontaneously where the Higgs field, the invisible energy field that gives particles their mass, drops to its lowest possible energy state. In that moment, the fundamental constants that govern reality shift, and this bubble begins expanding outward at the speed of light. By the time you saw the wall of annihilation coming, it would already be too late. One moment, stars burn, chemistry works, life exists; the next, everything is rewritten into something unrecognizable. This isn't just speculation. The Higgs field we know might be metastable, like a ball resting in a shallow valley instead of at the bottom of a deep pit. A strong enough nudge, and it could roll down into a lower energy state, triggering a phase transition that sweeps across the cosmos. The math suggests it's possible, though unlikely. In fact, calculations indicate our vacuum might have survived purely by chance for billions of years, perched precariously on the edge of stability. Could human experiments accidentally push it over the edge? The Large Hadron Collider at CERN has been scrutinized for this very risk, with some theorists questioning whether high-energy particle collisions might create the critical conditions for vacuum decay. Thankfully, the consensus is clear: cosmic rays with far higher energies bombard Earth constantly without triggering catastrophe. If nature hasn't done it in 13.8 billion years, our machines probably won't either. But the real terror of vacuum decay isn't its likelihood, it's its inevitability. If the Higgs field is metastable, the laws of quantum mechanics say decay isn't just possible, it's guaranteed. Given enough time, a random quantum fluctuation anywhere in the universe could spark the bubble. The only comfort, space is so vast that it might take googles of years before it happens. Or it could start tomorrow. What makes this threat so chilling is its absolute indifference. No warning, no defense, just physics obeying its own rules, erasing galaxies as casually as a wave washing away footprints in the sand. And yet, there's a strange beauty in knowing even the vacuum of space isn't truly empty, but seething with potential energy, waiting to redefine existence itself. For all our fears, vacuum decay reminds us that the universe isn't just dangerous, it's profoundly, unpredictably dynamic, capable of reinventing itself in ways we can scarcely imagine. Rogue planets are the universe's drifters, frozen, starless worlds cast adrift in the interstellar void, untethered from any sun. These nomads of the cosmos don't just wander, they're capable of rewriting the fate of entire solar systems with a single, careless pass. Imagine an Earth-sized planet, dark and icy, barreling through space at hundreds of thousands of miles per hour. No sunlight warms its surface, no auroras dance in its skies, just endless cold and silence. But its gravity is far from silent. One of these rogue worlds drifting too close to our solar system could unleash chaos. Its gravitational pull might yank comets from the Oort cloud, that distant shell of icy debris surrounding us, flinging them inward like a cosmic slingshot. The result, a hailstorm of comets crashing through the inner solar system, with Earth caught in the crossfire. Evidence suggests this nightmare scenario might have happened before. Around 13,000 years ago, the Younger Dryas impact hypothesis proposes a barrage of comets or asteroids triggered a mini-ice age, wiping out megafauna like mammoths and destabilizing early human civilizations. Could a rogue planet's fly-by have been the unseen hand behind that catastrophe? Then there's the more direct threat, collision. Without a star to anchor them, rogue planets follow chaotic, unpredictable paths. In 2012, astronomers discovered CFBD SIR 2149, a rogue world just 100 light-years away, drifting alone through space. If something like it entered our solar system, the gravitational ripple effects could destabilize planetary orbits, turning our stable cosmic neighborhood into a celestial demolition derby. Even a near miss might tug Earth into a new, harsher orbit closer to the Sun for a global inferno, or farther out for an eternal winter, the most chilling prospect. We might not see it coming. Rogue planets emit almost no light, and current telescopes struggle to spot them unless they pass directly in front of distant stars. Some estimates suggest there could be billions of these free-floating worlds in the Milky Way alone, outnumbering stars by as much as 20 to 1. Among them might be Planet 9, the hypothetical giant some astronomers believe lurks in our solar system's outer reaches. If real, its gravity could explain the bizarre orbits of distant objects like Sedna. But if it's not bound to our Sun, if it's just passing through, its influence could one day turn from curiosity to catastrophe. Yet rogue planets aren't just agents of destruction. Some might harbor subsurface oceans kept liquid by radioactive decay or tidal heating from ancient moons. In the abyss of interstellar space, these dark, frozen worlds could be arks for life, carrying extremophile microbes between stars. They remind us that the universe doesn't play by our rules. A planet doesn't need a sun to be significant, just the right trajectory at the wrong moment, and a lone wanderer could rewrite history. The cosmos is full of such silent travelers, and we're only beginning to grasp their power. At the heart of the Crab Nebula, a 1,000-year-old stellar corpse spins faster than a kitchen blender 30 times every second, hurling beams of radiation into space with terrifying precision. This is the Crab Pulsar, a neutron star so dense it packs the Sun's mass into a sphere the size of Manhattan. But its true danger lies in the invisible storm it whips up around itself, the Pulsar Wind Nebula, a maelstrom of charged particles accelerated to nearly the speed of light. Picture a cosmic hadron collider wrapped around a dying star, where electrons spiral through magnetic fields so intense they glow with X-rays visible across 6,500 light-years. The pulsar wind isn't just energetic, it's apocalyptic. Those charged particles carry enough punch to strip away planetary atmospheres or fry spacecraft electronics in seconds. If Earth drifted into this radiation bath, the effects would make a nuclear meltdown look like a sunburn. Satellite communications would fail instantly. Power grids would surge and collapse, and any astronaut caught outside protective shielding would absorb a lethal dose of radiation in minutes. The pulsar's beams sweep space like a lighthouse from hell, and if one ever pointed directly at us, the torrent of gamma rays and X-rays would ionize our upper atmosphere, triggering continent-wide blackouts and ozone depletion that could last decades. What makes the Crab especially menacing is its youth. Most pulsars slow down as they age, their winds weakening over hundreds of thousands of years. But this one's a toddler in cosmic terms, just 960 years old, and still raging with the energy of its supernova birth. Chinese astronomers recorded that explosion in 1054 as a daytime star visible for weeks. Today, we see the aftermath. A nebula expanding at 4 million miles per hour, its filaments glowing with the light of annihilated matter. And at its core, the pulsar's wind generates shocks so violent they've been caught flaring in X-rays, releasing more energy in minutes than our Sun does in years. Yet for all its fury, the Crab Pulsar is also a cosmic gift. Its precise beams act as a universal clock, helping astronomers test Einstein's relativity with unparalleled accuracy. The nebula's tangled magnetic fields serve as a lab for studying particle acceleration, offering clues about how cosmic rays, the mysterious high-energy particles zipping through space, are born. Even its deadly winds play a role in galactic ecology, seeding the universe with heavy elements forged in supernova. It's a reminder that the universe's most dangerous engines are often its most productive, a paradox as beautiful as it is terrifying. So while we're safe for now, the Crab's death beams thankfully aimed elsewhere. It's a vivid demonstration of how precarious our cosmic neighborhood really is. One wrong spin of a stellar corpse, and the sky could turn from a canvas of wonder into a weapon of unimaginable power. And somewhere out there, other pulsars are spinning, their winds carving invisible kill zones through the galaxy. The universe doesn't just harbor life, it's littered with hazards that could erase it in a blink. Buried at the core of nearly every massive galaxy lies a cosmic particle accelerator of unimaginable scale, an active galactic nucleus, or AN. These aren't just supermassive black holes quietly slurping down gas. They're voracious engines surrounded by swirling disks of plasma so hot they glow with the light of billions of suns. But the real showstopper is what happens when some of that material escapes the black hole's grasp. Instead of vanishing forever, it gets funneled into jets of plasma stretching millions of light years into space, moving at nearly light speed. These aren't gentle streams, they're galactic fire hoses blasting particles with energies that make Earth's most powerful colliders look like children's toys. Take M87, the first black hole humanity ever imaged. While its shadow made headlines, the real spectacle is the jet erupting from its core, a 5,500 light-year long spear of plasma twisting through space like a cosmic lightning bolt. The particles inside that jet are accelerated to such extreme energies that they emit light across the entire electromagnetic spectrum, from radio waves to gamma rays. If you could stand next to it and somehow survive, the jet's radiation would deliver centuries worth of the sun's total output in mere seconds. The physics behind these jets is both beautiful and terrifying. As matter spirals toward the black hole, magnetic fields get wound up like cosmic rubber bands, storing unimaginable tension. When they finally snap, they launch material outward along the black hole's spin axis, channeling it into those narrow, ultra-focused beams. The process is so efficient it converts matter into energy with 10 times the efficiency of nuclear fusion, a stellar powerhouse on steroids. Now imagine one of these jets pointing directly at Earth. Even from thousands of light years away, the gamma-ray burst alone could trigger mass extinctions by shredding our ozone layer. Closer in, and the particle bombardment would ionize the atmosphere, turning skies into a glowing haze of toxic nitrogen oxides while surface radiation levels spiked to lethal doses. Entire continents could be bathed in auroras bright enough to read by, a dazzling prelude to ecological collapse. Yet AGNs aren't just destroyers, their jets act as intergalactic pollution control, heating up vast regions of space and preventing gas from cooling too quickly, a cosmic thermostat that regulates star formation across entire galaxy clusters. Without them, the universe might have burned through its star-forming fuel billions of years ago, leaving no raw material for planets or life. Astronomers now suspect that AGNs flicker on and off over cosmic timescales, depending on how much gas falls into their gravitational traps. Our own Milky Way's central black hole, Sagittarius A star, is quiet now, but scans of its surroundings reveal fossil jets evidence of past outbursts when it too was an active galactic nucleus. One day, as galaxies collide and fresh gas arrives, it could awaken again. Until then, we study these titans from a safe distance, humbled by their power to shape the universe on scales we can barely comprehend. White dwarfs are the smoldering embers of dead stars, Earth-sized cores of carbon and oxygen left behind when sun-like stars exhaust their fuel. But pack two of these stellar corpses into a tight orbit, and you've got a cosmic time bomb ticking toward one of the universe's most spectacular detonations. When white dwarfs spiral into each other, their collision doesn't just spark a supernova, it unleashes a Type Ia explosion so brilliantly consistent that astronomers use it to measure the cosmos itself. Yet behind that useful precision lies raw destructive power capable of sterilizing entire star systems. The math is terrifyingly elegant. As the white dwarfs circle each other, they lose energy through gravitational waves, inching closer with each orbit. Eventually, one star begins stripping material from its partner, piling stolen matter onto its own surface like a celestial thief. but there's a limit about 1.4 times the Sun's mass where the accumulating weight triggers runaway nuclear fusion. Carbon ignites like a stellar powder keg, detonating with such force that both stars are obliterated within seconds. The resulting explosion outshines entire galaxies, blasting out heavy elements like iron, nickel, and cobalt at speeds exceeding 10,000 miles per second. History witnessed such an event in 1572, when Tycho Brahe spotted a new star in Cassiopeia so bright it rivaled Venus in broad daylight. That supernova, now called Tycho's star, was a Type Ia explosion just 2,300 light-years away, close enough that its light temporarily cast shadows on Earth. Had it occurred within 50 light-years, the radiation would have bathed our planet in enough X-rays to trigger mass extinctions. What makes these mergers uniquely dangerous isn't just their brightness, it's their aftermath. The explosion spews out enough iron to forge thousands of Earths, along with radioactive isotopes like nickel-56 that keep the supernova glowing for months. This toxic debris permeates interstellar space, poisoning future star systems with heavy metals. Astronomers have even detected traces of these elements in meteorites, remnants of our own solar system's birth in a cloud enriched by such explosions. Yet without these catastrophic mergers, life as we know it couldn't exist. The very iron in our blood, the calcium in our bones, all were forged in the hearts of dying stars and scattered by supernova. Type Ia explosions serve as both creators and destroyers, their light guiding our understanding of cosmic expansion while their debris lays the groundwork for future worlds. The universe has a dark sense of irony. The same detonations that could erase civilizations also provide the building blocks for new ones. And somewhere out there, another pair of white dwarfs is slowly spiraling toward oblivion, destined to remake their corner of the cosmos in fire and metal. When two neutron stars spiral toward each other in a deadly dance, their collision doesn't just create a spectacular explosion, it rewrites cosmic chemistry in a heartbeat. The event known as a kilonova is the universe's ultimate alchemy lab, where the heaviest elements in existence are forged in a firestorm of nuclear reactions. Take GW 170817, the first kilonova ever detected through both gravitational waves and light. When these two city-sized stellar corpses, each weighing more than our Sun, finally merged 130 million light-years away, the resulting fireball unleashed more energy in 1 second than our Sun will emit in its entire 10-billion-year lifetime. The physics behind this cataclysm is staggering. As the neutron stars circle each other thousands of times per second, tidal forces begin shredding them apart, ejecting jets of neutron-rich material at nearly light speed. In this maelstrom, free neutrons bombard atomic nuclei at unimaginable densities, building elements atom by atom through rapid neutron capture, the R process. Gold, platinum, uranium, every precious metal and radioactive isotope heavier than iron owes its existence to these violent cosmic collisions. The GW 170817 event alone is estimated to have produced over 10 Earth masses of gold, flinging it into space like celestial treasure. Yet for all their creative power, kilonovas are also engines of destruction. The merger's gamma ray burst beams radiation across space with surgical precision, and if one of those beams pointed at Earth from within 10,000 light-years, the effects would be catastrophic. The initial gamma-ray flash would strip our ozone layer within hours, exposing the planet to deadly ultraviolet radiation for years. Worse still, the expanding debris cloud carries radioactive fallout like iodine-129 and plutonium-244, with half-lives measured in millions of years. A nearby kilonova could bathe our planet in a slow poison, rendering surface life unsustainable for generations. Remarkably, we might already bear scars from such an event. Geological records show a puzzling spike in radioactive isotopes around 1.5 million years ago, potential evidence of a kilonova explosion within our cosmic neighborhood. Ocean sediment layers contain elevated iron-60, an isotope typically forged in supernova or kilonovas, suggesting Earth may have weathered a close call during the Pleistocene epoch. What makes kilonovas truly humbling is their duality. They're both creators and destroyers on galactic scales. The same explosion that could sterilize planets also seeds future star systems with the building blocks for rocky worlds, and perhaps life itself. Every gold necklace, every uranium fuel rod contains atoms born in these apocalyptic collisions billions of years ago. We're literally made of stardust, but some of that dust carries the fingerprints of the universe's most violent reunions. And somewhere in the cosmos right now, another pair of neutron stars is inching toward oblivion, preparing to light up the darkness with gold-filled fire. Cosmic strings sound like something straight out of theoretical physics, and that's because they are. These bizarre relics of the early universe are thought to be cracks in space-time itself, formed fractions of a second after the Big Bang when the fabric of reality underwent violent phase transitions. Picture the universe cooling like a molten piece of glass, developing microscopic flaws as it solidified. These flaws, stretched to astronomical lengths by the expansion of space, became cosmic strings, filaments thinner than a proton but with the mass of entire galaxies packed into every inch. The math behind them is mind-bending. A single cosmic string could weigh 100 billion tons per centimeter, yet be no wider than a quark. That density warps spacetime so severely that passing near one would be like skating across a frozen lake with an invisible whirlpool beneath you. Time would slow down on one side of the string and speed up on the other, creating a gravitational lens effect so extreme it could split light from distant stars into duplicate images. And if a string were to pass straight through Earth, it wouldn't just slice our planet like a cosmic scalpel, it would leave behind two perfectly cleaved halves, their edges fused by the string's gravity as if nothing had happened. Then there's their movement. Cosmic strings aren't static, they whip through space at nearly light speed, vibrating like snapped guitar strings. When two strings cross or a loop pinches off, the resulting energy release could outshine quasars, briefly flooding the cosmos with gravitational waves. Some theorists even suggest these events might explain bizarre cosmic phenomena like fast radio bursts, those mysterious, milliseconds-long energy pulses from deep space. What makes cosmic strings truly unsettling is their longevity. Unlike black holes or neutron stars, these defects don't evaporate or decay. Once formed, they could persist for eternity, drifting through the cosmos like invisible garrots. A galaxy that encounters one might find its stars rearranged overnight, their orbits scrambled by the string's gravitational wake, and because they emit no light, we'd have no warning before one entered our solar system, just sudden, inexplicable distortions in the paths of planets and comets. Yet for all their destructive potential, cosmic strings might also be the universe's ultimate time capsules. Their very existence could reveal secrets about the Big Bang's first moments, offering clues to forces that shaped reality before atoms even formed. Some models suggest their gravitational signatures might one day be detectable through subtle twists in the cosmic microwave background, the afterglow of creation itself. Until then, they remain both a tantalizing theory and a silent reminder. The universe doesn't just harbor dangers we can see. Some of its deadliest threats are flaws woven into the fabric of existence, waiting to be pulled taut. If active galactic nuclei are the universe's particle accelerators, then blazars are those accelerators aimed straight at Earth, cosmic railguns firing relativistic jets directly in our direction. Among these celestial flamethrowers, Markarian 501 stands out not just for its power, but for the chilling demonstration it gave us in 1997. Normally a quiet emitter of gamma rays, this blazar located 450 million light-years away suddenly flared with such intensity that it doubled the muon count in Earth's atmosphere for days. Those muons, heavy cousins of electrons normally created by cosmic rays, bombarded the planet in numbers unseen before or since. Had Markarian 501 been 10,000 times closer, a cosmic stone's throw on galactic scales, the effects would have been apocalyptic. The mechanics behind this are brutally efficient. At the blazar's core, a supermassive black hole weighing perhaps 1 billion suns spins furiously, its accretion disk funneling matter into twin jets of plasma. By pure cosmic misfortune, one of those jets points directly at our solar system, turning what would normally be a distant curiosity into a potential extinction-level event. The particles in those jets don't just travel fast, they're accelerated to 99.9% the speed of light, gaining energies that dwarf anything produced in human-made colliders. When these particles smash into Earth's atmosphere, they trigger cascades of secondary radiation, turning the very air into a diffuse shower of ionizing particles. A closer blazar wouldn't just increase muon counts, it could plunge Earth into a prolonged artificial winter. The relentless particle bombardment would ionize the upper atmosphere, seeding clouds that reflect sunlight back into space while allowing lethal UV radiation to penetrate. Crops would fail as global temperatures plummeted, and the ozone layer stripped away by the blazar's radiation would take decades to recover. Unlike a supernova or gamma-ray burst, the damage wouldn't come in a single catastrophic flash, but as a creeping, inescapable siege lasting years. What makes blazars especially unsettling is their unpredictability. Markarian 501's flare wasn't preceded by warning signs, just a sudden surge in activity that left astronomers scrambling for explanations. Other blazars, like the infamous Bielaceae, fluctuate wildly in brightness, their jets flickering on and off like cosmic strobe lights. We can't predict when the next major flare will occur, nor can we rule out that an even more violent blazar lurks undiscovered in some quiet corner of the sky. Yet for all their destructive potential, blazars are also invaluable cosmic laboratories. Their extreme physics helps us test the limits of Einstein's relativity, while their jets act as natural telescopes, magnifying light from even more distant objects through gravitational lensing. They remind us that the universe doesn't distinguish between wonder and terror sometimes. The same phenomenon that could erase life also helps us understand the fabric of reality. And that duality is perhaps the most humbling lesson of all. In the grand cosmic arena, we're both observers and potential targets, dancing on the edge of forces beyond comprehension. Before the first stars ignited, before galaxies took shape, the universe may have birthed monsters unlike anything we see today. Dark stars, celestial behemoths fueled not by nuclear fusion, but by the annihilation of dark matter. Picture a star 1,000,000 times more massive than our Sun, its core seething with particles of invisible matter colliding and dissolving into pure energy. Unlike ordinary stars that shine through hydrogen fusion, these primordial giants would glow with an eerie, ghostly light, their surfaces radiating heat from a process we've never witnessed directly. The physics behind them bends reality. In the early universe, dense clumps of dark matter, those mysterious, gravity-creating particles that outweigh normal matter 5-to-1, could have gathered normal gas like cosmic sponges. As the gas condensed, dark matter particles trapped in the star's core would collide and annihilate, releasing enough energy to keep the star puffed up and luminous for millions of years. The result, a ballooning sphere of hot plasma, cooler at its edges than a modern star but far larger, potentially stretching wider than our entire solar system. What makes dark stars truly unsettling is what they might leave behind. If some survive to the present day, their cores could have collapsed into dark matter cinders, objects hotter than the sun's surface, emitting streams of exotic radiation that warp normal matter on contact. Imagine a rogue dark star drifting unnoticed through our galactic neighborhood, its invisible emissions subtly disrupting the chemistry of nearby planets. Molecular bonds might weaken inexplicably, metals could corrode at accelerated rates, Life on a world bathed in this dark radiation might find its very biology unraveling, a silent catastrophe with no visible source. The hunt for these relics is already underway. Telescopes scour ancient galactic regions for infrared signatures that match theoretical models' unusual heat without the expected light. Some researchers even suggest that certain ultra-dense stellar corpses, like neutron stars with unexplained heat signatures, might actually be the fossilized hearts of dead dark stars, their dark matter fuel nearly spent but still smoldering. Yet for all their destructive potential, dark stars could hold keys to the universe's deepest mysteries. Their existence would prove dark matter can interact with itself, a clue to its true nature. Their remnants might even explain the universe's missing antimatter. If dark matter annihilation favors matter over antimatter, it could hint at why we live in a cosmos dominated by the stuff we're made of. They're cosmic paradoxes, potential harbingers of apocalypse, and yet perhaps the architects of our existence. The universe has always balanced creation and destruction, and dark stars may be its most haunting example yet. Primordial black holes sound like relics from a science fiction nightmare, tiny, ancient, and unimaginably dense remnants of the Big Bang itself. Unlike the massive black holes formed from collapsing stars, these could be as small as a grapefruit, yet packed with the mass of an entire mountain. Picture a black hole no bigger than a basketball drifting silently through space, its gravity so intense that light can't escape from just millimeters away. Now imagine one of these cosmic bullets passing straight through Earth. What unfolds would be a slow-motion disaster of biblical proportions. The moment it enters our atmosphere, the black hole's immense gravity would start pulling matter inward at nearly light speed. Air molecules, dust, even birds and planes caught in its path would spiral toward it, heating up to millions of degrees as they compress into a glowing, high-energy plasma tail. But the real horror begins when it reaches the ground. As it tunnels through the planet's crust, the black hole would trigger earthquakes with every mile traveled, its gravitational wake distorting rock like a ship's prow cutting through water. Cities above its path would crumble as the ground liquefies, swallowed by tremors far beyond anything in recorded history. Yet the damage isn't just gravitational. Thanks to Stephen Hawking's groundbreaking work, we know black holes aren't perfectly dark. They leak energy over time in the form of Hawking radiation. For a primordial black hole, this isn't a slow trickle but a deadly signature. As it moves, it emits high-energy particles like a radioactive comet, scorching everything in its vicinity with X-rays and gamma rays. Anyone within miles of its trajectory would receive lethal doses of radiation in seconds, while the land itself would become a barren wasteland. And then comes the finale. If this black hole has been slowly evaporating since the dawn of time, losing mass through Hawking radiation, its final moments would be cataclysmic. Once it shrinks to a critical size, the remaining energy bursts free in an explosion equivalent to 500 megatons of TNT. To put that in perspective, that's 10 times the power of the most powerful nuclear weapon ever detonated, concentrated in a single, shattering instant. The blast would vaporize everything within a 20-mile radius, leaving a crater deeper than the Grand Canyon and sending shockwaves rippling across continents. The chilling reality, we might not even see it coming. Primordial black holes are nearly invisible unless they're actively consuming matter, and current telescopes can't scan for objects this small lurking in the dark between stars. Some theories suggest they could be hiding in our solar system right now, drifting like unseen landmines. Others propose they might even make up part of the elusive dark matter that haunts our universe. What makes them so fascinating and terrifying is their duality. They could be both destroyers and cosmic fossils, offering clues about the universe's violent birth while posing a threat we're only beginning to understand. If one exists and if it crosses our path, the damage would be unstoppable. but until then, they remain one of space's most enigmatic puzzles, reminding us that danger doesn't always come in sizes we can easily see. Sometimes the deadliest things in the universe fit in the palm of your hand. Most stars glide through the galaxy in orderly fashion, tracing gentle orbits around the Milky Way's center. But HIP 85605 is different. This rogue is speeding toward us like a cosmic wrecking ball. Current projections suggest that in roughly 240,000 years, it will scream past our solar system at a mere 0.04 light-years away, just over 2,000 times the distance from Earth to the Sun. To put that in perspective, that's closer than any known star has come in recorded history, closer even than Proxima Centauri is today. What makes this stellar interloper so dangerous isn't the flyby itself, it's the gravitational ripple effects. As HIP 85605 barrels through the outer edges of our solar system, its gravity will act like a bull in a celestial china shop, jostling the Oort cloud. This distant shell of icy debris, stretching nearly a light-year from the Sun, is home to trillions of comets, many of them barely held in place by the Sun's weak gravitational pull. The passing star's tug could send thousands of these icy missiles cascading inward, turning the inner solar system into a shooting gallery. We've seen this horror movie before. 4 billion years ago, the late heavy bombardment pummeled the young Earth and its neighboring planets with asteroids and comets, leaving scars like the Moon's craters as grim souvenirs. Some theories suggest a similar stellar flyby triggered that ancient cataclysm. If HIP 85605 replicates the event, the consequences would be apocalyptic. Imagine Halley's Comet arriving every week for millennia, each impact releasing energy equivalent to millions of nuclear bombs. Oceans would vaporize, continents would fracture, and the resulting dust clouds could plunge Earth into a centuries-long winter, a second genesis for all but the hardiest extremophiles. Yet HIP 85605 isn't some abstract future threat, it's already on the move. Astronomers tracking its trajectory note it's traveling at nearly 25 kilometers per second relative to our Sun. Its path calculated through precise parallax measurements from Gaia, the European Space Agency's star mapping satellite. The star itself is a modest orange dwarf, smaller and cooler than our Sun, but its velocity transforms it into a cannonball. Here's the chilling twist: this might not even be the closest future encounter. Recent simulations suggest other stars like Gliese 710 could pass even nearer in the next million years. The universe, it seems, is far more crowded and far more volatile than we once imagined. Every passing star, no matter how distant, tugs subtly at the delicate web of orbits holding our solar system together. And HIP 85605 is just one of many cosmic reminders that our peaceful corner of the galaxy is anything but permanent. For now, we're safe. 240,000 years is an eternity by human standards, but the star's approach serves as a sobering lesson. The solar system isn't an isolated island. It's a dynamic system constantly nudged by unseen forces. In the grand timeline of the cosmos, stellar close calls aren't rare, they're inevitable. And one day, far in the future, another rogue star will take aim. The only question is whether civilization will still be here to see it coming. Intergalactic space seems empty, just vast stretches of nothingness between galaxies. But that emptiness makes it the perfect stage for one of the universe's most underrated threats, the intergalactic supernova. Unlike their galactic cousins, which explode surrounded by gas clouds that absorb some of their fury, these lone detonations unleash their full force unchecked. Picture a star dying in the void 100,000 light-years from any galaxy, its shockwaves racing through space with nothing to slow them down. If one erupted too close to Earth, the radiation blast would arrive like a silent tsunami, carrying enough energy to rewrite life itself. The danger lies in the unfiltered cosmic rays, high-energy particles accelerated to nearly light speed by the explosion. Normally, the Milky Way's magnetic fields and interstellar gas diffuse these particles, weakening their impact. But in intergalactic space, there's no such buffer. A supernova out here would fire a focused beam of ionizing radiation straight through whatever crosses its path, including our planet. The effects would be insidious, not instant. Over months, the radiation would bombard Earth's atmosphere, penetrating deep into the soil and water. DNA strands in every living organism would accumulate mutations faster than repair mechanisms can handle, triggering waves of cancer, sterility, and birth defects across species. We've seen glimpses of what could happen. Fossil records hint at past extinction events linked to radiation spikes, like the mysterious Devonian Carboniferous die-off 359 million years ago, when terrestrial plant spores suddenly SHOWED, Chinese letter deformities, a possible fingerprint of cosmic ray damage. Even today, astronomers detect occasional supernova remnants floating between galaxies, their shockwaves still rippling through the void after millions of years. The chilling reality is that we might not see the threat coming. A solitary star could collapse unnoticed in the darkness, its light too faint to trigger alerts until the cosmic rays are already upon us. Telescopes like Fermi's Large Area Telescope scan for gamma-ray bursts, but an intergalactic supernova's particle barrage could arrive with little electromagnetic warning, like a sniper's bullet from the cosmic shadows. Yet these explosions aren't just agents of destruction, they're also cosmic distributors. The same rays that could devastate life also carry trace elements forged in the supernova's heart, seeding the universe with the ingredients for future stars and planets. It's a paradox as old as time. The forces that create are often the ones that destroy, and somewhere in the void, another star is nearing its end, poised to remind us just how thin the line between life and oblivion really is. Deep within particle accelerators like the Large Hadron Collider, scientists probe the boundaries of reality, sometimes brushing up against theoretical nightmares. Among these is strange matter, a hypothetical form of quark goo so stable it could rewrite ordinary atoms on contact. Picture a single drop of this substance, known as a strangelet, accidentally created in a high-energy collision. Within nanoseconds, it begins converting everything it touches, protons, neutrons, even the very table it rests on, into more strange matter. The domino effect would spread outward at light speed, transforming Earth into a lifeless, hyperdense sphere no larger than a soccer field. This isn't just sci-fi fantasy. Strangelets arise from legitimate physics, specifically the idea that under extreme pressure, matter might stabilize into a strange quark soup rather than the protons and neutrons we know. Normally, quarks, the building blocks of particles, exist in triplets, but in the crushing depths of neutron stars or particle colliders, they could theoretically reorganize into bulk strange matter, a state where up, down, and strange quarks mingle freely. The danger: if this substance is more stable than normal matter, as some models suggest, it could act like a cosmic virus, propagating indefinitely. CERN takes the risk seriously enough to have built multiple safeguards. The relativistic Heavy Ion Collider in New York and the LHC in Switzerland both screen for strangelet signatures in collision debris, watching for abnormal energy signatures or particle tracks. So far, no evidence exists, and most theorists argue the conditions needed to spawn stable strangelets are absurdly unlikely. The universe has been running its own particle collisions via cosmic rays for billions of years. If strange matter were this contagious, the cosmos would already be overrun. Yet the stakes are high enough to warrant caution. In 2008, a lawsuit even attempted unsuccessfully to halt the LHC over strangelet fears. The irony is rich. The same machines probing the origins of the universe must also guard against inadvertently ending it. For now, strangelets remain a fascinating what if, a reminder that the frontier of discovery sometimes skirts the edge of destruction. And perhaps that's the price of unraveling the universe's deepest secrets, peering into the abyss, knowing some doors might be better left unopened. Imagine two supermassive black holes, each billions of times heavier than our Sun, locked in a final death spiral. As they collide at nearly light speed, they don't just merge, they send shockwaves through the very fabric of spacetime itself, unleashing a gravitational tsunami powerful enough to stretch planets like taffy. These are the cosmic tremors LIGO first detected in 2015, rippling across 1.3 billion light-years from the merger of black holes 30 times our Sun's mass. But what if such an event happened closer, say, within our galactic neighborhood? The results would be less scientific curiosity and more existential nightmare. The physics behind these waves is deceptively simple yet terrifying in scale. As the black holes orbit each other, they distort spacetime like bowling balls rolling on a trampoline. In their final moments before merging, they whip this cosmic fabric at frequencies matching the human body's resonant frequency, the same principle that makes opera singers shatter wine glasses. For us, the danger isn't just the stretching, it's the shaking. At close range, gravitational waves would vibrate your internal organs at their natural frequency, turning hearts and lungs into liquid oscillators. Bones would resonate like tuning forks before snapping, while the brain, floating in fluid, would experience something akin to being microwaved from within. LIGO historic detection proved these waves carry enough energy to momentarily warp Earth's shape by a fraction of a proton's width across 4 kilometers of laser beam. Now scale that up to supermassive black holes, the kind lurking in galactic centers. Their mergers release gravitational waves with the combined energy of 100 million supernova, enough to briefly outshine every star in the observable universe. A merger within 10,000 light-years might not just liquefy organs, it could trigger global earthquakes, alter Earth's rotation, or even nudge the planet into a new orbit over centuries through cumulative gravitational nudges. The terrifying twist, these events are happening right now in distant galaxies. Supermassive black hole binaries form when galaxies collide, and astronomers have already spotted candidates like those in Quasar OJ287, where two cosmic titans orbit each other every 12 years. Given enough time, all galactic cores may face similar fates. For now, we're protected by the vastness of space. The nearest potential merger, in galaxy NGC 6240, sits 300 million light-years away. But the universe is old and space is big. Somewhere out there, another pair is spiraling toward catastrophe, preparing to shake the cosmos with ripples that bend reality itself. Perhaps most unsettling is how little we'd sense the danger coming. Gravitational waves travel at light speed, offering no advance warning. One moment, everything's normal. The next, the very ground beneath your feet starts breathing like a living thing as spacetime itself heaves. Yet these waves also carry secrets about the universe's most violent events, secrets we're only beginning to decode. Every ripple LIGO catches is a message in a bottle from the abyss, written in the language of warped spacetime. And that's the paradox of gravitational waves. They're both destroyers and messengers, capable of unraveling worlds while teaching us how the universe works. We think of dark energy as the universe's mysterious push, an invisible force stretching space faster and faster, ensuring galaxies drift apart forever. But what if this force isn't uniform? What if certain regions of the cosmos harbor dark energy in concentrated pockets where its repulsive gravity runs wild? This nightmare scenario, known as a dark energy overdensity, could shred the fabric of the cosmos far sooner than any big rip prediction. Evidence for this lurks in one of astronomy's most puzzling anomalies, the cold spot. Found in the cosmic microwave background, that faint glow from the universe's infancy, this region spans nearly 2 billion light-years and is noticeably colder than its surroundings. While some argue it's just a statistical fluke, others see fingerprints of a dark energy overdensity. a cosmic void where repulsive forces have accelerated expansion so violently that photons stretching across it lose energy, leaving a cold imprint. Now imagine such a pocket forming near our local group of galaxies. Unlike the gradual expansion we observe today, this would be a runaway reaction. Space itself would stretch at catastrophic speeds within the overdensity, overcoming even the gravitational glue holding galaxies together. Stars on the outskirts of the Milky Way would first redshift into invisibility as space between them and us expanded faster than light could traverse it. Then, as the effect reached inward, spiral arms would unravel. Solar systems would be flung into the void, planets torn from their orbits. Finally, even atoms would rip apart as the space between nuclei expanded faster than the strong nuclear force could bind them. The terrifying part, we'd have no warning. Dark energy doesn't emit light or interact with matter. We only infer its presence by its effects on cosmic expansion. A growing overdensity could already exist just beyond the observable universe's edge, its influence creeping toward us at the speed of causality. And unlike the Big Rip, which gives the universe tens of billions of years to prepare, a dark energy overdensity could regionalize doomsday, leaving most of the cosmos untouched while annihilating our corner in a cosmic blink. Yet this phenomenon isn't purely destructive. If overdensities exist, they might solve the Hubble tension, the discrepancy in measurements of the universe's expansion rate. Local variations in dark energy density could explain why some observations suggest faster expansion than standard models predict. They'd also imply dark energy is dynamic, evolving in ways we've yet to comprehend, rather than the static cosmological constant Einstein once imagined. For now, the cold spot remains a mystery, and dark energy overdensities purely theoretical. But telescopes like Euclid and the Vera Rubin Observatory are hunting for subtle distortions in galaxy distributions that might betray these invisible killers. Whether they find them or not, the search forces us to confront an unsettling truth. The universe's acceleration isn't just a gentle tide carrying galaxies apart. It could be a riptide lurking in patches, ready to drag entire structures into the abyss. And that changes everything we thought we knew about how the cosmos will end. Quantum singularities lurk in the darkest corners of theoretical physics, black holes stripped of their event horizons, their infinite density laid bare for the universe to see. Without the cosmic veil of an event horizon to shield us, these naked singularities defy the very laws of physics as we know them. Picture standing too close to one. Time stutters like a broken record, looping forward and backward without warning. Space twists into knots, turning left into up or past into future in a chaotic dance of distorted reality. This isn't just gravity run amok. It's the total breakdown of predictability, where the equations that govern our universe simply snap under the strain. Einstein's theory of general relativity hints at their existence, but even he dismissed them as mathematical oddities too absurd to be real. Yet modern simulations suggest they might form under extreme conditions, like the collapse of a rapidly spinning star where centrifugal forces could rip away the event horizon, exposing the singularity beneath. Unlike their well-behaved black hole cousins, naked singularities wouldn't play by the rules. A black hole's event horizon acts as a cosmic one-way door, ensuring whatever falls in stays in. But remove that barrier and all bets are off. Radiation, matter, even causality itself could come spewing back out in unpredictable bursts, rewriting local physics like a malfunctioning computer program. The consequences of encountering one would make a black hole seem tame. Approach a traditional singularity, and you'll hit the event horizon before anything truly bizarre happens, spaghettification aside. But a naked singularity, you'd witness the impossible long before crossing any point of no return. Clocks might tick erratically, running faster for your feet than your head due to extreme time dilation. Light could bend into infinite loops, creating Hall of Mirrors illusions where you see the back of your own head from every angle. Even the concept of forward loses meaning as space itself fractures into recursive knots. What makes these objects truly unsettling is their potential to rewrite the universe's rulebook on the fly. Near a naked singularity, the fundamental constants that govern reality, the speed of light, the strength of gravity, even the charge of an electron might fluctuate wildly. Chemistry, as we know it, would become impossible with atoms warping into unstable configurations. Life, if it could exist at all in such a place, would be a nonsensical patchwork of momentary coherence in a sea of chaos. The hunt for these cosmic anomalies remains one of astrophysics' greatest challenges. Since they emit no light, we'd need to spot their gravitational fingerprints, strange distortions in spacetime that can't be explained by black holes or neutron stars. Some researchers speculate that fast radio bursts, those mysterious millisecond flashes from deep space, could be the death throes of naked singularities flickering in and out of existence. Others suggest they might explain dark matter's missing pieces, their gravitational pull detectable even if their true nature remains veiled. Yet for all their destructive potential, quantum singularities also represent a frontier of discovery. They could be portals to new physics, revealing hidden layers of reality beyond Einstein's equations. Some theories even propose they might bridge universes, their infinite density punching holes in the fabric of spacetime itself. Whether they're cosmic glitches or keys to a grander theory, one thing is certain. In a universe where the rules seem fixed, naked singularities are a reminder that some things refuse to play by them. And that's what makes them so terrifying and so fascinating. Hidden in the cosmic shadows between stars, there might be entire asteroids made of a substance so volatile that a chunk the size of a baseball could flatten a city. Antimatter. Unlike ordinary matter, where electrons orbit atomic nuclei, antimatter flips the script. Its atoms contain positrons, the antimatter counterparts to electrons swirling around antiprotons. When matter and antimatter meet, they annihilate each other in a flash of pure energy, converting their entire mass into gamma rays with 100% efficiency. To put that in perspective, just 500 grams of anti-iron colliding with Earth would unleash energy equivalent to the Hiroshima bomb, all from something that could fit in your hand. The hunt for these cosmic bombs took a startling turn in 2017 when the Alpha Magnetic Spectrometer, a particle detector mounted on the International Space Station, sniffed out traces of anti-helium in cosmic rays. Anti-helium nuclei, each composed of 2 antiprotons and 2 antineutrons, should be vanishingly rare in our matter-dominated universe. Yet MS-02 detected them, sparking whispers of a mind-bending possibility. Could these particles be fragments from antimatter asteroids or even entire antimatter stars lurking in the void? Here's the nightmare scenario. Imagine an antimatter rock the size of a mountain drifting undetected into our solar system. Unlike regular asteroids, it wouldn't reflect sunlight or leave a visible trail, just a faint haze of gamma radiation as stray atoms in the interstellar medium brush against it and annihilate. By the time our telescopes spotted the telltale energy signatures, it might already be too late. A direct impact would release energy orders of magnitude beyond any nuclear weapon, while even a near miss could bathe Earth in a lethal shower of gamma rays as the asteroid's outer layers erode in the solar wind. The origins of such objects are as fascinating as they are terrifying. Some theorists suggest they could be remnants of the early universe, when matter and antimatter nearly annihilated each other completely, leaving behind scattered pockets of antistuff. Others propose they might form in the extreme environments around pulsars or black holes, where raw energy condenses into anti-atoms just as easily as normal matter. There's even speculation about entire antiplanets or antistars hiding in galactic voids, their light indistinguishable from ordinary stars until you tried to land on one, a fatal mistake. What makes antimatter asteroids uniquely unsettling is their stealth. A typical asteroid impact gives us years or decades of warning as telescopes track its orbit. But an antimatter interloper, unless it plows through a dense gas cloud or ventures close enough for its annihilation glow to stand out against the cosmic background, it might slip through our defenses entirely. The AMS-02 findings hint that these invisible killers could be more common than we thought, each one a cosmic landmine waiting to detonate. Yet for all their destructive potential, antimatter objects also hold tantalizing clues about the universe's deepest mystery. Why does anything exist at all? The Big Bang should have created equal parts matter and antimatter, leaving nothing but energy after their mutual annihilation. That we're here means some asymmetry tipped the scales in matter's favor. Studying stray anti-helium nuclei could reveal what tipped that balance and whether antimatter worlds are really out there, floating in the dark like mirror images of our own. Until then, every unexplained gamma-ray flicker in the night sky keeps astronomers awake, wondering if they've just glimpsed the universe's most perfectly camouflaged doomsday weapon. From rogue black holes that lurk unseen between galaxies to the quantum nightmares of strange matter and naked singularities, the universe operates on a scale of violence that defies comprehension. Each of these cosmic threats carries its own brand of destruction, whether it's the slow, invisible decay of vacuum collapse rewriting reality itself, or the sudden, searing fury of a gamma-ray burst sterilizing planets light years away. The sheer diversity of these dangers is humbling. Some creep toward us over millennia, while others could erase us in an instant without warning. And yet, here we are, a species of curious, determined explorers, scanning the heavens not just out of fear but wonder. What makes our pursuit so extraordinary isn't just the technology we've built to detect these threats, telescopes that catch whispers of gravitational waves, satellites that track the death throes of distant stars. It's the audacity to face them head-on. Every gamma-ray burst we catalog, every pulsar wind we map, every dark matter filament we trace adds another layer to our cosmic defense. Knowledge, in the end, is our only real shield against the chaos of the cosmos. The same black holes that could shred stars also power quasars whose light guides our understanding of the early universe. The same neutron star collisions that might one day bombard us with lethal radiation also forged the gold in our jewelry and the uranium in our reactors. So while the universe may be indifferent to our existence, that doesn't mean we're powerless. Every new discovery, every mission launched, every theory tested brings us closer to unraveling the mysteries that could one day save us. The night sky isn't just a gallery of horrors, it's a classroom, a laboratory, a challenge waiting to be met, and that's where you come in. Stay curious, stay engaged, and keep looking up. Because the universe is dangerous, but understanding it is our best defense. Subscribe now to dive deeper into the cosmic mysteries that shape our past, present, and future. The next revelation could be the one that changes everything.